Let's look at a new topic, a Green's function. Let's look at where this Green function is coming from and how can it be useful. So let's start by a relatively simple ODE is a second order linear, non-homogeneous, and the right hand side is the Dirac delta function, computed at t-2. We apply the Laplace transform to look for the particular solution. So as before, we don't care about the initial conditions at all, we just get rid of them. So we have that capital XS is the fraction of the exponential of e at the minus 2s divided s squared minus 1. And we can split 1 over s squared minus 1 into 1 over 2 times 1 over s minus 1 minus 1 over s plus 1. This is the partial fraction approach. With the partial fraction, we have that xt is the inverse Laplace of capital S, so it's 1 over 2, inverse Laplace of e at the minus 2 times our partial fraction. And here, I want you to remember that the Laplace transformation of the Heaviside function times any function with both of them shifted by t minus a is the exponential of minus at times the Laplace transform of f. That means that when we're going back and using the inverse Laplace, if we have an exponential of some form, well, we can just apply it as the Heaviside function and the shift. So we're going to have that the Laplace transform of e at the minus s2s times something is equal to the inverse Laplace of that something calculated at t minus 2 times the Heaviside function at t minus 2. So the inverse Laplace of what we had in our dots in there, that, if you remember, was this 1 over s minus 1 minus 1 over s plus 1, is e at the t minus e at the minus t, but because of the shift that we have applied before, we have this minus 2 appearing in both times. So let's generalize. Let's replace 2 by a tau, and we have that 1 over 2 doesn't change because that was coming from the fact that our split in the partial fraction gave us a 1 over 2, but in the exponents and in the shift of the Heaviside function, instead of having t minus 2, now we have t minus tau. Because t and tau always appear together, and in this like t minus tau fashion, we can define this as being the Green's function of t minus tau. We call this the Green's function for x squared minus x, x second derivative minus x. So we have constructed this solution for x second derivative minus x equals the Dirac's function. Let's look at a general function on the right hand side. We rewrite this f of t as the integral from 0 to t of the convolution of f and delta. I encourage you to test out the fact that indeed this equation is right. And if this is the case, then when we're doing our Laplace transform, we can do the Laplace transform of the convolution. Remember, is the product of the two Laplace transforms. So we gain this e at the minus s, and fs being the Laplace transform of f. So we can find the Laplace transform of our solution x, depending on exponential. There should be no tau in the exponential, times f of s divided s squared plus 1. And then the solution is the inverse. Remember that the inverse Laplace of a product is a convolution of the inverse Laplaces. So we have the inverse Laplace of our right-hand side convoluted with the inverse Laplace of e to the minus s divided s squared minus 1. But the inverse Laplace of e to the minus s divided s squared minus 1 is exactly the thing we computed before and that we defined as being the Green's function. And this is a general statement. When you're solving for an equation, if you solve first for the Dirac's, for like replacing the right-hand side by the Dirac's function, you will find the Green's function, and you can replace that inside. You can find the general solution as the convolution of your right-hand side times the Green function. The Green's function, just to make it clear, is the solution of the ODE when the forcing term is the Dirac's delta. If you know the Green function, with the Laplace transform and convolutions, you can find all particular solutions. In particular, the particular solution is equal to the convolution of your forcing term and the Green's function.